Hello everyone, this paper is entitled Bluetooth Low Energy and CNN-based Angle of Arrival Localization in Presence of Rayleigh Fading. This paper is a collaborative research between Concordia University and University of Toronto, which is accepted in IEEE International Conference on Acoustics, Speech, and Signal Processing. In this presentation, first I want to talk about the motivation and contribution of this paper. Then I want to talk about our proposed CNN-based AoA localization framework. Then I want to talk about our simulation results and conclusion. As we know, there are different indoor localization frameworks based on different features of the received signal, like RSSI, angle, and time-based localization frameworks. In this paper, our focus is to use angle-based localization frameworks. And as we know, one of the commonly used angle estimation algorithms is subspace-based methods that requires a complex multipath mitigation model to provide an accurate localization framework. So for this reason, the focus has shifted to data-driven approaches such as those based on deep neural networks. However, recent deep neural network models just consider the effect of noise, and since we know that there are multiple obstacles in indoor environment, it is very possible to establish non-line of sight links between the transmitter and the receiver, which is modeled by Rayleigh channel model. In this paper, we consider a BLE-based indoor localization framework in a 3D indoor environment, which is affected by noise, which is modeled by AWGN with different signal to noise ratio, and Rayleigh fading channel. Then we apply convolutional neural networks for location estimation. This figure illustrates the block diagram of the proposed CNN-based AoA localization. The first three blocks shows the transmitter, the wireless channel, and receiver of the BLE that you can find more equations in the paper. In this paper, we assume that there are four BLE beacons in the environment, and when a signal is transmitted by the user, this signal can be received by all these beacons with different angles. For using the CNN model, first we need to prepare the data that I will completely describe this block in the next slide. And then we have a CNN model. Here, the input of the CNN is angle images, and the output of the CNN is a location of the user. And in this figure, you can see the experimental data collection and an angle image. As I mentioned earlier, there are four BLE beacons in the environment. So for each location, we will have four BLE signals received by different beacons. But by using the original BLE signals, we cannot estimate the location. So we need to extract angle information from these signals. For this reason, we use a special spectrum and actually the subspace-based models. And in the second figure, you can see the spatial spectrum of the received signal by different beacons. And here you can see that the minimum values of the spatial spectrum gives us the angle of the incident signal. And the last figure shows the angle image, where the x-axis shows the number of BLEs, and the y-axis shows the spatial spectrum of the received signal. And here you can see our simulation setup. Our experimental testbed consists of four BLE beacons and Viken cameras positioned at the corner of a rectangular indoor environment divided into 81 square zones. The data which is generated is based on three different channel models. The first one is AWGN model, where SNR is between 10 and 20 dB. The second one is based on Rayleigh fading channel, and the last one is a combination of AWGN and Rayleigh fading in a 3D indoor environment. Our CNN model consists of two-dimensional convolution layers, each with 190 6 filters with 4 kernel size. We use maximum pooling layers and utilize sigmoid as an activation function. Finally, within the dense layers, we use linear function as the activation function. And here you can see the number of angle images for training, validation, and test phases. And here you can see our simulation results, and you can see that by increasing the number of epochs, the accuracy increases and the loss decreases, which shows that the model is well trained. And you can see that the proposed CNN-based AoA framework can track mobile users with the accuracy of about 87% in the presence of noise, Rayleigh fading, and elevation angles. And here you can see two different scenarios, rectangular and random trajectories. And based on different models, the CNN-based AoA scheme, the 3D music, and the true flight position obtained by beacon cameras. And you can see here in both scenarios, the estimated passes by the proposed CNN-based AoA framework is almost the same as the true flight positions. And as a conclusion, we propose an efficient CNN-based AoA localization framework in a 3D indoor environment with application to BLE standard. And the experimental results showed that the proposed framework provides accurate results even in the presence of noise with different SNRs, a Rayleigh fading channel, and elevation angle. Thank you for your consideration.